All right. So welcome everyone to this week's edition of Paleo Perks, where we're very excited to have Drew Christ from the University of Vermont, who will be presenting a talk titled The Story of Camp Century, the Fossil Ecosystem Under Ice. Before we get to Drew's talk, just a quick reminder or introduction if you're new to the format of today's seminar. So we'll do this quick welcome and announcements right now, and then we'll get to Drew's talk. And following the talk, we'll have a moderated question and answer session. And then Drew has agreed to stick around for tea time after the question and answer session. So we encourage everyone to stick around afterwards and have a more informal chat with Drew and anyone else who decides to stick around. So during the talk, if you have questions that you'd like us to ask Drew at the end, feel free to send them to the questions at PaleoPerks host via the chat, who I believe today is Elizabeth. So some quick housekeeping things. PaleoPerks values the participation of everyone interested in the paleosciences, so please remember to abide by our code of conduct during today's seminar. You agreed to it when you signed up. If you found yourself here without having signed up for the mailing list, you can check out the mailing list or sign up for the mailing list on our website and quickly look over the code of conduct as well. So please also keep yourself muted for the duration of the talk. And following the talk, as we said, you can ask questions by chatting to the questions at PaleoPerks host, or if you'd rather, by using the raise hand function, and we'll unmute you then if you want to ask your question out loud. Additionally, if you have any technical issues during the talk, you can send those via the chat to the questions at PaleoPerks host as well. So we now have built into Zoom. You should be able to use the CC button to show or hide them. Additionally, we're always looking for nominations for other early career speakers, and we'll drop the link for where you can nominate someone in the chat. Also into the chat, we'll drop our weekly feedback form that just collects demographic information so we can get an idea of who's attending. It's anonymous, optional, and encouraged. So please fill that out really quickly as you see it pop up in the chat. So today's speaker, as we mentioned, is Drew Christ, who is currently a postdoc at the University of Vermont after having got his undergraduate at Hamilton College and a PhD at Boston University. And Drew is going to talk to us about some ecosystems under ice. So if you want to take over the screen share, Drew, I'm really excited to see what you've got for us.
All right. Awesome. Thank you so much. And thanks to the organizers for putting on such a great series. It's really wonderful to see all these people from around the world sharing their research, and getting to be amongst other early career researchers is really great because it feels like a good space where we can all share our ideas and support each other. So thank you guys so much for organizing. So today I'm going to be talking about the Camp Century ice core, specifically the sediment from the very bottom of it and the fossil ecosystem that we found in that sediment. So before I get too far along, I just want to acknowledge that this is a project that has been made possible by many, many different people who are either contributing samples or analyses or just expertise in ice core science. And so this is really a huge team effort, and I'm just very privileged and lucky to get to work with these people and learn from them. So you can't talk about Camp Century without talking about history, because the whole reason that Camp Century exists is because of the Cold War. And so at the height of the atomic age during the Cold War, the Arctic was the closest path between the Soviet Union and the United States. And so there was a huge worry that there were going to be intercontinental missile strikes shot across the Arctic Ocean from the Soviet Union to the United States. This led up to a military buildup among the NATO nations in the Arctic, and the US military, with permission from Denmark, built a large Air Force base in Thule in northwestern Greenland, where they installed this early detection missile warning system that is still there today. And so as the US military was building up military operations in the far north, they started to do some kind of wacky things. And among the craziest things that the US Army did during that time was build Camp Century, which was this city under the ice. So in the late 50s, the Army started hauling heavy equipment with snowcats across the Greenland ice sheet, about 100 miles into the interior from Thule, and started digging a series of tunnels into the actual ice and snow to build a military base. And this military base was sold to the public as a Arctic research laboratory, where the military was learning how to perform and adapt in challenging Arctic conditions. And this was highly public to the Americans and other Western nations through popular media, like National Geographic, Popular Science. They even brought up Walter Cronkite, the CBS News anchor, to do a 30-minute long news film about Camp Century. And because this was the atomic age, they also decided to power this base with a small nuclear reactor. And that could support up to about 100 soldiers, engineers, and scientists. Now, the real reason behind why the US Army was interested in building this base was that there was this project, or secret mission rather, called Project Iceworm, where the military was devising a way to build a series of railway tunnels inside the ice sheet so that they could store and hide nuclear weapons from the Soviets. So the Army very quickly learned that that was not possible because, as we know, ice sheets are these flowing masses of ice that deform over time. And so as they were occupying the base, they started to realize that the walls were starting to collapse in, either from the ductile deformation of the ice itself, as well as the really high snowfall rates from above that were starting to crush buildings. So after 1966, they abandoned the base, and only a few years later, they went back and saw that this tunnel that was feet wide was now only about 4 feet wide because everything started to compress. So while this was this kind of crazy Cold War science fiction-esque project, they were actually doing some incredible basic science at Camp Century. And one of those projects was studying the ice sheet itself. And they collected the very first ice core drilled through the entire thickness of an ice sheet at Camp Century. And the analysis of that ice core really revolutionized how we understand Earth's climate over the last 100,000 years. Within the ice core, we were able to see the entirety of the Holocene, the last deglaciation, the last glacial, and all the interstadials and rapid climate changes during the last glacial period, back into the last interglacial. And then at the very bottom of the ice core, they recovered basal ice and sediment. So about 16 meters of debris-laden or sediment-rich ice, and at the very bottom, about 3.5 meters of frozen sediment. So the ice core, the actual ice, was studied intensively and extensively, but these basal materials were not studied very much, and then they were actually lost for decades. So they were initially in the US at the University of Buffalo until the late 80s, early 90s, and then they were shipped over to Denmark to the Niels Bohr Institute, where they kind of just sat in a cold, dark freezer for the last 30 years until they were rediscovered during an ice core inventory. And so the group of scientists I'm working with, we were all kind of tapped to come in and supply analyses for these. And my advisor here at UVM, Paul Bierman, who specializes in cosmogenic nuclides, thought that this would be a great project for me to work on during my postdoc. And it turned out to be a really incredible project because we didn't really know just how cool this was going to be. So this story of Camp Century isn't just a story about the city under ice, it's really the ecosystem under ice. And separated by almost 60 years, we are able to go and look at the basal sediment from Camp Century, shown here with the original ice core scientists, Lyle Hansen and Chet Langway, back at this Pentagon little photo op in the late 60s, to me working on the exact same sample of sediment over 50 years later. And what we discovered is that it contains fossil plants and biomolecules from ancient tundra from at least 2 ice-free events in the past. Once in the early Pleistocene and another in the last million years. And we have some new data that tells us when that last event may have been. So this Camp Century sediment is really a time capsule because it tells us a tale of a warmer Greenland when the ice sheet was smaller than it is right now. And this, of course, is important as we look to the future as humans continue to warm the climate and melt the Greenland ice sheet. In the next couple of centuries, if we continue on our business as usual, burn all of the fossil fuels in the ground approach, we could melt significant portions of the Greenland ice sheet and raise sea level as much as 3.74 meters. So we want to understand the future, right? What is the fate of the Greenland ice sheet? So we can look to the geologic past. And specifically, we want to know, when did parts of the Greenland ice sheet melt away? From, the geologic record, we're beginning to see that the Greenland ice sheet has been dynamic, but persistent on Greenland for the last several million years. It's more or less been there, but there have been times when it has retracted in size. So we can look at the marine record, which are continuous records with oftentimes better age control. But these are indirect measures of what the actual extent of the ice sheet is, right? They're proxies. So ice rafted debris can tell you about how much ice, if there's ice terminating into the ocean and the volume of ice rafted debris being delivered out into the marine realm, as well as sea surface temperature and summer temperature reconstructions from micropaleontology and leaf waxes, as well as looking at the palynology and sediment composition off of southern Greenland, which gives us an idea of whether or not southern Greenland was ice covered or not. Now, the other way that we can look into the deep time record of the Greenland ice sheet is to look at ice core basal materials. These can directly tell you whether or not those locations were covered by ice in the past, but it's been really challenging to get good geochronology on these archives. But what we have right now is an emerging picture that the Greenland ice sheet must have been absent within the last million years. And we know this because at the center of the Greenland ice sheet at GISP-2, the subglacial bedrock must have been exposed within the last 1.1 million years, and that's using cosmogenic nuclide dating. We also have some evidence from the Di-3 ice core in southern to be boreal forests there, and there's a ancient DNA analysis of that basal ice that contains flora and fauna from boreal forests. So it's beginning to look like the Greenland ice sheet must have been smaller at some point in the last million years, but the timing and the extent of those ice sheet retreats is poorly known. So we can go to Camp Century up here in the far northwest portion of the ice sheet to understand, another data point from this, uninvestigated subglacial sediment. And another reason it's important to go to this part of Greenland is that it's near the margin. So this is one of the parts of the ice sheet that is going to melt earlier than other parts of the ice sheet and raise sea level. So we want to know the ice sheet history of this part of Greenland and the ice sheet sensitivity to past climate change. So The Camp Century subglacial sediment contains 2 units of Diamectin, which is a poorly sorted mixture of sediment small grain sizes and lithologies that's separated by a sediment-rich ice layer. And what we have been working on so far is the very uppermost sediment from near the ice sediment interface, sample 1059, and another piece of sediment from the very bottom of the core, 1063. So what evidence of IceFree conditions does this sediment contain? So the first way that we can think about this is by examining the pore ice stable isotopes. And the pore ice stable isotopes are enriched. Sorry, that was, there may have been a gray box hiding some stuff. Sorry about that. The pore ice delta 018 is enriched relative to all the overlying ice in the ice core and modern precipitation at Camp Century. So modern precipitation is about -29 per mil. And in the pore ice of this sediment, we saw values of -23 and -21.5. And if you plot these values against all of the Del 018 values that are measured in the ice core, it's plotted far to the right to more positive numbers, which implies warmer conditions, much warmer than anything we see in that ice. So if you were to interpret that just as a temperature change, we would see values that are just way too warm for Camp Century to have an ice sheet at it, right? It would be impossible to have such. Explain this enrichment is actually through a net elevation lowering caused by the absence of the ice sheet and isostatic rebound. So I'll walk you through how we get to this. So right now, you have precipitation falling at Camp Century with Del 018 of about -29 per mil. The surface elevation is almost 1,900 meters. Beneath the surface is about 1,400 meters of ice to bedrock at 500 meters. Now, if you removed the ice sheet, the crust would isostatically rebound and cause the bedrock to rise up. So you would end up with a net elevation change of 940 meters. That elevation change can account for about 5.3 per mil of the enriched values. And then the remaining enrichment in Del 018 could be attributed to slightly warmer temperatures. This is all to say that the pore ice Del 018 values imply precipitation at lower elevations that require the absence of the ice sheet. And then the most obvious evidence for an ice-free event preserved in the sediment was the discovery of macrofossils in the sediment itself. And so it was a kind of a crazy day for me. It was 5 days before my PhD defense, which had nothing to do with this project at all. And we had gotten this sediment, and I was a little bit stressed out, as you might understand, ahead of your defense. And I was like, do we really need to work on this today? And, you know, we're in the lab, we're wet sieving this sediment to sort it for other analyses. And we see these black specks floating in the rinse water as we're wet sieving. And Paul and I pick up a disposable pipette and suck up one of those black specks and look at it under the microscope. And we just saw a twig. And we were like, oh my God, we weren't expecting to find plants in this sediment. We just totally blown away by it. And it was one of the most exciting days of science, probably of my life. And just one of those true eureka moments that I didn't really think happened, but it did happen. So what we've been learning from these macrofossils is that we found mosses and leaf tips and twigs and fungal spores from tundra plants found in ice-free areas of Greenland today. We analyzed the leaf wax in the sediments, and they have distributions similar to modern Greenland shrubs. And we recently have examined these pieces of woody tissue under a scanning electron microscope, and we've determined that it's mostly Arctic willow. We have better preservation of the macrofossils in the upper unit of Diamectin, and there's a greater abundance of them too. It took several hours to pick through all of these different twigs. It really, I guess a funny way to think of it is like if you've gone on a hike or a trek and you get a bunch of like twigs and stuff in the bottom of your hiking boot and you like pour it out at the end of the day, there's like a bunch of it, right? And it kind of looked like that when we were picking this out of the sediment. It just was endless. We wanted to know how old the sediment is. And the first thing that we did was take one of the twigs and radiocarbon date it, and it returned an infinite age greater than 50,000 years. So we know that this material is quite old. But really the question is, how old is the sediment? So we have a couple of ways that we do this. The first way I'll talk about is using cosgenic nuclides, beryllium-10 and aluminum-26. These nuclides are produced in quartz in the near upper 2 to 3 meters of surface materials in quartz. And over time, they accumulate in the crystalline lattices of quartz. But if you were to produce both aluminum-10 and aluminum-26 and beryllium-10, they have a ratio at the surface between 6.7 and 7.3. But if you then advance an ice sheet over that, over the landscape, nuclide production stops. They're hidden from those cosmic rays. And then because they're radionuclides, they begin to decay. So the total inventory of nuclides decays and the ratio of aluminum to beryllium decreases from that initial value of about 7.3. In using that decay rate and the ratio of these two different nuclides, we can determine the maximum duration of burial in sediments. So that's one way that we did this. Now, the other way that we can determine the age of these sediments is using luminescence dating, which essentially answers the question, when was the sediment last exposed to light? I'm not a luminescence expert, but I'm going to give you just an overview of how this works because it was new to me. So luminescence dating relies on the idea that when sediments are buried beneath the surface and hidden from sunlight, the background radiation in sediments and soils will excite electrons that will fill in the crystal lattices, the impurities in the crystalline lattices in different minerals like quartz and feldspar. And over time, that will accumulate a luminescent signal. But if you expose that sediment to sunlight, it bleaches the electrons out. So you lose the luminescent signal. If you bury it again, that same idea happens again. You accumulate those electrons in the holes in the crystalline lattices from the background radiation. But in some minerals like feldspar, you actually have a little bit of fading. Some of those electrons are released out. And then geologists, we have to sample this in the dark. So you can't expose the sediment to sunlight, otherwise you're going to reset your clock. Now, if this didn't make sense to you, you can think about wearing dirty clothes. If you just wore the same shirt every day for a month, it would accumulate a stinkiness index, right? Stinkiness signal. But if you put it in the washer, it's going to not be stinky after about a few minutes. Then if you wear that same shirt again for a month, it's going to accumulate that stinky signal. That's kind of the same idea with luminescence dating. So what are the ages that we get with these two different methods? I'll start with the lower Diamectin, which is much older. Using aluminum beryllium burial dating, we know that it has been buried no more than 3.2 plus or minus 0.4 million years. With the infrared luminescence dating on feldspars, the last light exposure was before 0.7 million years ago, but more likely before 1.4 million years ago. This lower Diamectin may record an early advance of the Greenland ice sheet. So in this figure, I am showing the last 4 million years with some different paleoclimate indicators that are relevant to Camp Century global mean sea level and Siberian temperature at the Lake E sediment core. And so if we place these age constraints of the lower Diamectin from Camp Century, we see that it is correlative with the very early beginnings of the fully expanded Greenland ice sheet, starting about 2.6 million years ago. The presence of the tundra twigs and leaf tips and mosses in this sediment are the oldest record of vegetation recovered below the ice sheet so far. Now, what about the upper sediment? Well, the upper sediment has very different age constraints. So that tells us there are two different episodes of ice-free exposure and burial below ice. I'll start with just discussing the cosgenic nuclide constraints on the upper Diamectin, which requires exposure within the last 1.0 to plus or minus 0.1 million years. This new age constraint gives us quite a bit of confidence that the Greenland ice sheet has melted and reformed at least once in the last 1.1 million years. Because all of the ice core basal materials from the interior and to the south, they're all younger than 1 million years old. So there is nothing at the bottom of these ice cores that tell us that the ice has been present for longer than 1 million years. And then I want to focus in on Camp Century versus GISP-2. And GISP-2 is in the very interior of the ice sheet, just near the summit, whereas Camp Century is near the margin. Now, these two different archives, the subglacial sediment and the subglacial bedrock, have similar aluminum-beryllium ratios, and that suggests a similar burial history. But the maximum burial age requiring exposure in the last 1 million years at both sites is really great evidence that this ice sheet has disappeared in that time frame, suggesting a similar history of ice cover between the margin and the interior. Now we have better age constraints on the upper Diamectin because we were able to get some infrared luminescence dates that we've been collecting or measuring over the last few months or so with the help of Tammy Rittenauer at Utah State. And so we tried to get a robust data set from this sediment. So we used multiple aliquots, meaning analyzed multiple grains of feldspar in 2 different grain sizes of the same sample. So ultimately, we have nearly 40 measurements on grains that produce infrared luminescence ages of about 290,000 years. Now, if you remember, I mentioned that with feldspars, you have to correct for fading, and the fading measurements we collected suggest if you correct for fading, we get IRSL ages of about 391 plus or minus 28,000 years ago. These upper sediment luminescence ages require exposure and thus an ice-free event in the last 420,000 years. And we think that these IRSL ages are a robust data set because we have coherent ages in 2 grain sizes with multiple aliquots. We don't see any evidence of partial bleaching from exposure to sunlight. Otherwise, we'd see much larger spread in the data. And we don't think that this sediment is a mixture of sediments with different exposure histories because the data are so coherent. What does this mean in terms of paleoclimate? So if we place these age constraints from the IRSL ages against different paleoclimate records, without a fading correction, these ages fall into the MIS 8 glacial period. Now, that doesn't really make sense for an ice-free event to occur during the middle of a glacial period. So if we then consider the fading corrected ages, they date to just after the peak of the MIS 11C interglacial. So the fading corrected ages from the upper Diamectin correspond with a cooling climate after MIS 11C. I've zoomed in here on a time span of about between 450 to 250,000 years ago. And just to direct your eyes, here is the fading corrected age. And we can see that these fading corrected ages coincide with growing global ice volume from the benthic Diamectin stack, falling global sea level, declining carbon dioxide, a increase in ice raft to debris flux as the ice sheet got larger, as well as cooling sea surface temperatures, land temperatures, and the decline in pollen concentrations into the Labrador Sea south of Greenland, suggesting that the ice sheet was getting bigger. So these infrared luminescence ages actually record the re-advance of the Greenland ice sheet and burial of this sediment. We can use the infrared luminescence dating to support and further inform our cosmogenic nuclide burial history. It's a little bit of a complicated plot, but I'm going to try and walk you through it. So this is a 2-isotope diagram that we use in cosmogenic nuclides. Over time, on the x-axis, if you expose sediment, it's going to accumulate more beryllium-10. And if it's at the surface, but if you bury that sediment, those nuclides begin to decay and the ratio between them decreases. So these are the measured values that we got for the upper sediment and lower sediment. We can correct these for the burial time of 390,000 years to get an idea of what the burial history was at the end of the last exposure event. We can then simulate exposure simulations onto those sediments to tell us how long they could have been exposed. So you cannot expose this sediment, the upper sediment, for more than 14,000 years, or you end up with an initial burial history that suggests negative burial, which is impossible. So what this means, and then I'll talk about this in a second, but we can also correct for additional burial of that lower sediment, which we presume was not exposed during that last event. But what I want to take away from this plot is that that last ice-free event was no longer than 14,000 years. Or less than 14,000 years of ice-free exposure in Northwest Greenland aligns with sea level reconstructions during MIS 11C. So we have two different data sets that I'm just comparing this to that are based off of the benthic Diamectin stack, which both of them suggest that sea level was higher than present between 11,000 to 17,000 years of duration during MIS 11C. And so that 14,000 years of exposure at Camp Century is consistent with those durations. Now we need to know, where did this upper sediment come from? And I want to go back to our burial history again and see, if you correct that upper sediment for exposure during MIS 11 for up to 14,000 years and calculate what the incoming aluminum beryllium ratio is and compare it to the lower sediment, you see that they're very similar, which implies that they had a similar burial history to begin with. And that suggests to us that the upper sediment was sourced from material that was like the underlying sediment, that lower sample. We did a series of different geochronometry analyses on both sediments, and we see across different geochronometers that they have indistinguishable provenance, meaning that there was no major change in ice flow direction between the units. And it also suggests that that upper Diamectin material is similar to the lower Diamectin. Both of the sediment samples have really similar mineralogy, especially the bulk mineralogy, but they are slightly different in the heavy mineralogy between amphiboles and pyroxenes and garnets. And we think this may be reflective of a slightly different weathering history between the two units, which we've already observed in the pore ice ion concentrations and weathering clay grain coatings on each sediment that suggests that they had a different weathering history. So it suggests that the upper sediment may have been weathered more intensively than the lower sediment. So I just want to put this all together so we have some sort of schematic of what happened. This is showing just schematically the Greenland landscape and what we think was happening. We have an initial ice-free event where we have tundra growing sometime in the early Pleistocene. We have ice cover during much of the Pleistocene that entrains the lower Diamectin beneath the ice sheet with consistent ice flow direction. And then we have an ice-free event during MIS 11C at Camp Century with duration of no more than 14,000 years, with older local glacial sediment exposed and weathered. And then a re-advance of the ice sheet that entrained that upper Diamectin. Then, the Camp Century ice core is collected and recovered, in the last 60 years. So I'll wrap it up soon here, but if Camp Century is ice-free, how much ice does Greenland have to lose? Benjamin Kiesling has been doing some ice sheet modeling work to figure this out. And he ran 96 unique simulations varying a variety of parameters. And he found that in order to expose Camp Century, the configurations of the Greenland ice sheet require a contribution of at least 1.6 meters of sea level rise. So this is the most conservative configuration of the Greenland ice sheet that allows Camp Century to just barely be ice-free. And that requires at least 1.6 meters of sea level rise. It could be more, and there's a lot of spread in the data, but this is a hard bottom for that contribution. So big takeaway here is that the Camp Century sediment provides direct evidence for two ice-free events in Northwest Greenland. We have preservation of fossil ecosystems beneath the Greenland ice sheet. It seems that the Greenland ice sheet persisted through most Northwestern Greenland was deglaciated within the last 400,000 years, possibly during MIS 11, during an event that was no more than 14,000 years long. And in order for Camp Century to be ice-free, requires at least 1.6 meters of sea level contribution from Greenland. I just want to finish with one idea here why is MIS 11 such a special interglacial or warm interglacial that had such high sea level? And it was very long. It was 30,000 years long. So I just want to think more forward here is if the long duration of MIS 11C, 30,000 years, was long enough to melt a large portion of the Greenland ice sheet, what's going to happen if we continue to pump carbon dioxide into the atmosphere and it has a long residence time? So this is a recent review paper by Jess Tierney that was out earlier this year. And I really like this graph where she shows how much time it will take to reduce carbon dioxide concentrations back to 350 parts per million. And even under the moderate RCP emission scenario 4.5, it's going to take 30,000 years to get back to 350 parts per million. So if 30,000 years was long enough to melt Northwestern Greenland during MIS 11, what does that mean if we continue to warm the climate for very long periods of time? So last thing, we just got funded to do the remaining archive, analyze the remaining archive of the sediment, and we are recruiting a master's student to dive into some of the chemistry about the soil development, as well as weathering history. And you can contact me for more information about that. So sorry if I went a little bit over, but thanks so much for you all coming today, and I look forward to chatting with you.
Hey, thanks. So just a reminder that you can send your questions via the chat to, I got it wrong before, it's Natasha who is the questions at PaleoPerks host this week. So if you have any questions that you want to send, you can do that now. Or again, raise your hand if you'd rather try that way. And we've already got a few coming in. So let me put it into the chat really quick. So it says, this data set is so cool and it's really impressive how many aspects of Greenland How do you know whether the sediments slash macrofossils are from Camp Century's specific location, or do you think they could have been moved or dragged at the base of the ice sheet?
Good question. Yeah, the origin or the location of the origin of these sediments is something that is difficult to answer, but I have a couple of ideas about this. There's one line of evidence that suggests from geophysical measurements, radar measurements over the Greenland ice sheet, that there is a large lake basin in this part of northwestern Greenland that is hidden beneath the surface of the ice sheet. It's a extensional normal fault valley that has filled in with sediment, and it's unclear if it becomes a lake during ice-free events. And so it's possible that, this was kind of the environment that was there. It was this tundra ecosystem with ponds and lakes scattered across the landscape, kind of like we see in ice-free areas in Greenland today, at least in the more subpolar regions. I think that, they probably moved locally because the lower sediment and upper sediment have so many similarities in terms of their burial history, initial burial history, the geochronometry. That suggests to me that it is more or less local. Of course, it may have been transported a short distance. And then one more reason I think that they're relatively local to here is that the preservation of the fossils in the upper Diamectin it just seems too well preserved to have been transported a long distance, because I would imagine that long transport distances under flowing ice or wet-based, warm-based ice would destroy a lot of that material. So I think that it's mostly local, and that actually that much of the time it's been beneath the ice sheet, it's been cold-based glaciation, which is non-erosive. The basal borehole temperature at Camp Century when they drilled it was far below the pressure melting point. It was around -10 degrees C. So I think that it's more or less local to northwestern Greenland.
So there's another question that also showed up in the chat. Have you used any mutual climate range methods to look at what the flora tells you about climate?
We have not done that yet. And the ecosystem aspect of this project is still a work in progress, because number one, it was a shock. We weren't expecting to find this. And so we haven't been able to look at all of the sediment yet. So we haven't been able to get a full characterization of it. And then one more aspect of this project that is still in progress is some ancient DNA analyses of the sediment, which would give us a better holistic view of what's in it. And then we could start thinking about how to model it and bring it into climate models.
Yeah, should be fun. We have another question that I'll add in that says, such an interesting history and a great talk. You mentioned that there were biomolecules in the ice core basal material. Was this just DNA, or has there been any work done on lipids such as plant wax lipids? Pretty cool to find DNA though.
Yeah, so just this sediment, we have just done lipid biomarkers so far. And I didn't dive too much into it, but the concentrations of those lipids in the two different units are pretty different. And again, that upper Diamectin, there's a lot more of it, and it looks like they're better preserved than the lower, older sediment. So the DNA, we actually, it's in progress right now, but we have done the plant wax lipids.
So there's another question that maybe you sort of answered with your master's student recruiting, but what do you see as the next steps for this work?
Yeah, so I just got approval from UVM over the weekend to go to Copenhagen. And in very few short weeks, I'm going over there to help cut samples of the remaining archives to bring them back to UVM and begin processing them and distributing them to all of our collaborators. And that project is going to give us a much more overarching view of what's in these sediments, and it's going to allow us to get a better idea about cryostratigraphy that tells us about if there was the permafrost conditions that may have been preserved in the sediment. We're also going to be able to get a better understanding of how the sediment was mixed or transported by doing additional measurements on beryllium-10 and luminescence dating. And what's really cool about Diamectin and glacial tills is that they have minerals in them and at such large masses that you can do analyses that can be sometimes very difficult to do. So with cosgenic nuclide dating, you need a minimum of 20 grams of clean, pure quartz to make really high precision analyses. And oftentimes that can be really challenging to get out of sediments that are from the marine realm or river sediments that don't have a lot of quartz in them. But Diamectin, it's like we were able to get enough material to do really great analytical work on them. So I'm excited to see where this goes, and also to bring in a master's student who will get to hit the ground running.
Yeah. Let's see if I don't think I see any more questions. So if no one else has anything, I'll go ahead and take back the screen share. All right, so thank you, Drew, for a really cool talk, and thank you everyone else for joining us and listening in. So again, we'll put the weekly feedback form link back in the chat in case you haven't had a chance to fill that out yet. And please come back next week, same time, to hear Kate Lomedico-Marriott from Brooklyn College present on doing justice to the incredible biodiversity of ammonites, mathematical and visual perspectives. And so if you don't have to run away just now, please stick around for a more informal chat with Drew and anyone else who's got some time, and our little tea time session this week. So we can learn more about Drew and each other, and how we got where we are and all of that, and just chat with old friends or make some new friends and just see what everyone's up to. So with that, I'll start this little timer and see you all hopefully back in a couple of minutes after you've had some time to grab some water or stretch your legs. A little chat. All right, so thanks everyone, and see you in a bit.